and welcome to Top of the Flops, a rundown of the most popular experiments that tend to go wrong for teachers. In this programme, we'll show you what happens when things don't quite go according to plan and give you some top tips on how to make them go right. I've come here to CLEEPS, the School Science Support Service, to meet 3 chemists who'll be guiding us through our chart.
CLEEPS runs a helpline for teachers and technicians to ring in with any problems that they've got, things they need to find out about. And what we've done is we've had a look at the records of all the helpline calls that we've had and picked the ones that we get the most helpline calls about.
Many experiments teachers think are possibly banned, but indeed they're not. They can do them all with proper training and practice.
We're going to show you how to do things correctly and safely.
Excellent.
And still get a lot of enjoyment out of it.
We're conducting these experiments under carefully controlled conditions to show you what happens when they go wrong. So we don't advise you to recreate them. As well as the right methods, our team will be showing you some alternative approaches to some classic experiments. And kicking off our chart at number 10. Reacting copper oxide and magnesium powder. Straight underneath.
Right under the middle, yeah, on the hottest flame that you can get. Hot flame. Put this across. And then we need to take a step back.
Remember, this reaction can take anything up to 90 seconds. Doesn't seem to be doing much. Should we check it?
No. No. This is one that caught me out.
Really?
When I was...
Oh, wow.
It can go off when you're not expecting it to go off. That was a good one.
Oh, my God.
That's what I got wrong. I thought it hadn't gone off, and I went, as you did, to sort of maybe pull the Bunsen out or something, and it actually went off just as I put my hand in.
That could be so dangerous.
Yeah. That's why you need.
But also how
people...
tempting it is to kind of go and see,
it's like
check
a
on
firework, isn't it?
Yeah.
You just don't go back to it.
If you don't get a reaction, turn off the heat and wait for everything to cool. And at number 9, a classic, cracking hydrocarbons. But watch out for suckback. So Colin, what do we have here?
Well, this is an apparatus to basically break down a long chain hydrocarbon into a smaller hydrocarbon. We have a boiling tube which contains some aluminium oxide, and at the end of it is some mineral wool soaked in liquid paraffin. At the far end we have a delivery tube running down into this trough which is filled with water, and inside the trough are test tubes also filled with water. Now the idea of the experiment is that we heat up the aluminium oxide until it's really hot, and then we vaporise some of the liquid paraffin, which then moves over the aluminium oxide. It's broken down into a gas, and then it will escape through the tube at the end here.
Well, it's already starting to bubble.
Would you like to start collecting then?
What we're collecting here are gaseous hydrocarbons. The problems begin either when the heat is removed or when the paraffin is used up. Ooh, there seems to be something going back up.
It does, doesn't there?
Oh dear.
Well, that's what happens sometimes with this experiment. It's called suckback.
My goodness, so what just happened there?
We'd used all the liquid paraffin up, so there was no more gas coming out of the tube. So whatever was left in the tube just cooled down and created a kind of mini vacuum and sucked the water back up into the tube. It was then reacting with the hot material in there and causing a rather strange noise.
But that reaction's not as bad as it could get.
No, it could. Sometimes it happens that it's so bad that it cracks the tube.
So we're quite lucky this time.
Quite lucky this time indeed.
The right way is to remove the heat and immediately take the apparatus out of the water bath once the reaction is complete. Also at number 9, another common experiment at risk from suckback. It's heating copper-2 carbonate to produce carbon dioxide, which has bubbled through lime water. And once again, if you remove the heat,
it has cracked the test tube. As soon as you stop heating, you can either take the test tube away or take the delivery tube out.
okay. Heating in a hard glass test tube and using less lime water also reduces the risk of the experiment going wrong. At number 8, no, it's not banned, it's white phosphorus. So what's a common mistake that teachers make with phosphorus?
It's probably not a common mistake, but it is something that can go wrong and can be quite scary when it does. And it happened to me once when I was quite a young teacher, and I cut a piece of phosphorus and it leapt out onto the bench and actually just caught fire.
So can you recreate that experiment?
Yeah, we can. It's not something I would want to do very often. If we just put a tiny little piece of phosphorus on this heat-proof mat, you'll see what can happen. So, yeah, and that's what happens. And can you see some bits are actually spitting off, and you can get bits around, but it's quite a violent reaction.
Yeah. If this does happen, immediately cover the phosphorus to cut off the oxygen and contain the fumes. But there is a safe way to demonstrate white phosphorus reacting with air.
So long as it's underwater, it's quite safe. You need a fairly small slice.
Okay.
I'll
have a go.
It's actually like cutting a stick of rock.
It's really tough, isn't it?
Yeah, quite hard. Oh, well done. Brilliant.
The reaction takes place in a flask which contains air enriched with oxygen.
Brilliant. OK.
I'm using a heated glass rod to kick the reaction off.
All right, just vertically in and then lift the glass rod straight out. All right.
Wow.
Oh, and there's the clouds of phosphorus pentoxide.
It's quite a violent reaction.
Yeah, I mean, I did put a little bit of oxygen in there out of the cylinder, but mostly it was air. But that's the phosphorus reacting with the oxygen.
Wow, fantastic.
Yeah.
At number 7, never add water to concentrated sulfuric acid.
I have a tall form beaker here with about 1 centimetre depth of concentrated sulfuric acid. I've put a digital thermometer in the beaker. So now we're going to add a similar depth of water to this.
Okay. The acid starts at room temperature.
Wow.
Gosh. 137?
Yes.
Wow, that's really hot.
In the worst scenario, this can actually blow out over people.
The right way is to slowly add the concentrated sulfuric acid to water, preferably iced, mixing continuously. The temperature hardly changes. At 6, just missing out on our top 5, it's making iron sulfide.
What we've got is some iron powder and some sulphur powder. The first thing we need to do is get them really well mixed together.
Okay.
You any idea why we do it like this rather than...
It seems a bit cumbersome. Why?
Sometimes if you grind 2 powders together,
Yeah.
you get some heat from the friction.
Oh, right.
And it can
that could cause
trigger
a
off the reaction. Yeah. So what has to happen now is we'd have to give them a bit of heat to get the reaction to go. And one of the major things that people do wrong is they think they can do it on a tin lid. And I think we ought to have a look at why you don't do it like that.
So we're all set up in the fume cupboard.
Yeah. So iron sulphur mix on the tin lid. And all we need to do is get it hot with a blue flame and then see what happens.
Okay.
The sulphur's just caught light,
Oh,
the
wow.
blue flame.
Yeah.
And that means the sulphur's burning in the air, so you're getting lots of sulphur dioxide, which is a toxic gas. and there's the reaction between the iron and the sulphur.
Yeah.
And if you were doing that on an open bench,
It's hugely dangerous.
very
isn't it?
dangerous. Yeah.
So how do teachers cope without a fume cupboard then?
What you've got to do is try and trap the gases and stop the sulphur
Because that's the
catching.
dangerous part of this
Yeah,
experiment.
the SO2 gas, sulphur dioxide gas. So we've got the same amount that you had on your tin lid.
Yep.
Yeah. And what we can do is just put a bit of mineral oil plug
Oh, okay.
loosely in the end, and that'll just stop the fumes. And we should get the reaction to go. There, just go in now. So you can take the Bunsen away now, and it'll keep itself going. So that's the iron reacting with the sulphur,
Right, okay.
iron sulphide. And you can see all the fumes are trapped.
Into the top 5, and it's the old classic, making magnesium oxide.
This is a popular experiment carried out for GCSE where we investigate the increase in mass as magnesium burns inside that crucible. Now, I'd just like you to lift the lid carefully so that we let some air into the crucible
So not
and see
all
if
the
the
way off.
magnesium is alight.
The tongs make it hard to check the reaction easily. Whoa.
If you lift the lid for too long a time, magnesium oxide comes out, and that spoils the results in the end.
So if they can't lift the lid off the crucible, but they need to in order to see whether it's stopped burning brightly, how can they resolve that issue?
Well, we have got an alternative method which I can show you, involving beer bottle tops.
It's important to remove the plastic insert.
Onto the balance.
To prove the method works, I'm weighing the setup first.
4.75 grams. I'm going to make a little parcel, like that, with the opening just there,
Yep.
and then place the little nitro-wire tie over the top.
Okay. That just sits in there. Okay. So I guess the benefit of this setup is that you don't lose anything through the gaps in the bottle tops.
Yeah, that's right, and the students don't interfere with the apparatus.
Yeah. I think the students tend to interfere with it because they're trying to see what's happening inside.
That's right.
But you can see from the gaps that it's still burning.
After about 10 minutes strong heating like this, we can allow it to cool and see what the increase in mass is. And we get 4.93.
So it has gone up.
Yes, I think it's gone up just about the right amount as well.
Excellent.